Okay, but yeah, we're talking about entanglement. Well, I don't know what to call it really. I guess you could call it entanglement, but it's really just the quantum mechanics of multiple systems. And what we saw last time is the way you do it is you tensor product your system Hilbert spaces. They might have different dimensions. It could be when we do addition of angular momentum, it could be like the spin and orbital angular momentum Hilbert spaces. But in general, then you extend the notion of a ket that's part of one Hilbert space to just having a tensor product where you specify the ket in each component Hilbert space like that. And that's an element of this Hilbert space. That's a composite one. Maybe it's better to call this composite systems. That's really what we're worried about. And this tensor product is in itself a Hilbert space. This is, by itself, it's also some Hilbert space with dimension n times m. So we'll be doing spin 1/2 particles, putting them together. So the dimension there would be 2 times 2, which is 4. So it itself is a Hilbert space, so it must have an inner product defined on it. And the inner product is defined by the individual, the product of the individual inner products on the 2 Hilbert spaces. So I didn't emphasize this last time, but I think it's important. So the way you construct the inner product for the tensor product space is just you multiply the 2 inner products for the 2 subspaces like that. And then all of the same rules apply. Linearity and everything that it follows. So that was the setup. And where we left off last time is we were looking at 2 spin 1/2 particles. And so this is a 4-dimensional space. So our basis can be constructed from the combination of the bases for the 2 different spins. So there you go, it's 4 basis vectors for a 4-dimensional space. And the idea is that not all states, so what's a general state of the 2-particle system? The general state would be, right, arbitrary coefficients multiplying the basis elements. That's the general state. And the question you might wonder is, can we interpret the state as if it's just a combination of a state for system 1 and a state for system 2? And the answer is no, because imagine you did have such a thing. Well, what would that mean? Well, you would have some coefficients, right, for each individual state. I could write that as here, lambda 1, I guess, up arrow, plus mu1 down arrow, some decomposition like this. Of the 2 individual spins. And if I were to do the tensor product, what would I get? Well, I'd get lambda 1, lambda 2, up, up. Tensor product, you just multiply out these 2 kets with, again, there's an implied tensor product between the 2 spins. Sort of mentioned last time. And then you would get you would get the cross terms. So here is for spin 1, you get mu1, lambda 2. Spin 1 is down, and this one's up. And for the other cross term, you get lambda 1, mu 2. That's the one where the first one is up and the second one is down. And then you get down, down, which is mu 1, mu 2. Down, down. But if I look here, look, it's not, it doesn't always work. There's 4 unknowns here and 4 unknowns here, but it's over constrained because look, this guy and this guy, if I multiply them together, right, I get lambda 1, lambda 2, mu 1, mu 2. That would be the alpha delta coefficients. And then look at the ones in here, beta gamma. If I multiply beta and gamma together, I also get lambda 1, lambda 2, mu 1, mu 2 is equal to beta gamma. So it doesn't work. It means that to get a state like this, you require that alpha delta is equal to beta gamma in this general expansion. So not all expansions will work, right? It's too constrained. So not all states can be thought of as a decomposition into kets of the individual systems. And that's the nature of entanglement. Entanglement means that you can't think of the individual subsystems as having their own state that you could kind of measure independently of the state of the other system. That's basically the essence of it. But mathematically, you can see that general vectors inside the tensor product space do not have this form. They can be something else. They can be entangled. So that's the idea. Any questions about that before I do an example of an entangled state? No?
Yeah, so in previous lecture, you mentioned that the postulate 5 covered this over constraint, right?
Yeah, so postulate 5 is important because it does say that if you have 2 systems, then the Hilbert space for those 2 systems is this tensor product space. So a general state of these 2 spins is given by this form. But it doesn't mean that every single state in here you can think about as being a tensor product of 2 individual states for the 2 composite systems. But yeah, the postulate 5 tells you that everything has to have this form. That's what.
Yeah. So for the general state, can we write it as can we use the basis coming from the tensor product?
Yeah, so this is in the basis coming from the tensor product because we're summing over the basis of spin 1, which is up and down, and then the basis for spin 2 is up and down. So you get 4 possibilities. So yeah, you always have a basis that's made up of the tensor product of the individual space basis. So yeah, the basis for this guy is like n cross m for all possible n and m for those 2 spaces. Yeah, and what the postulate tells you is that even if the systems are interacting in some complicated way or something, anything that goes on, the whole system is still describable but by this Hilbert space. And it's just the weird thing about the Hilbert space is that not every single state in here you can write like this as just the tensor product of 2 individual states for the 2 subsystems. Some can be, and those are the not entangled states. And then the ones that can't be written this way are called entangled. And that's what entanglement is, really. It's not that mysterious if you just think about it in terms of the state of the composite system. But it does have mysterious properties, which is what we'll talk about now. So you do some example. of a entangled state. The classical one, it's the spin singlet, as it's called. So it's call it S. It's a linear combination of up, down, and down, up. It's called the spin singlet. We'll talk about singlets and triplets and all that when we deal with angular momentum. We'll go back to this. But for now, we just think about this as a state in our composite Hilbert space, and we can try to interrogate it, right? Remember that we had our rotation matrix for rotations in spin space, and this was sort of part of the multiple choice on the midterm. But we had this D matrix that would rotate an individual spin, and it had the following form. Had these I phi's over 2. Had these guys. We had this. So looks like a rotation matrix, but again, it's in the spin space, not like the 3D space that you're used to. It's in the space of the spin 1/2 state. So looks like that. And now we can, this is just like practicing working with tensor product space. The way you would normally do it is you just operate, on either one of the states. So an interesting thing to look at would be rotating the individual spins, right? Taking them and rotating them both at the same time, which would correspond to, a total rotation of the whole system. So you could, for instance, take this D1/2 and operate it on spin 1 and then also on spin 2. You could rotate both of them. So that's what we're going to do, just to show you how it works. And remember, this is all implied. This is implied that you rotate the first spin and do nothing to the second spin, right? And you just do them one at a time, and you just sort of see what happens. So we can try to do it on the up-down spin. So if we do it on the first, so let's apply the rotation on spin 1 first. What do we get? Well, spin 1 is pointing up. So that's the basis vector for that is 1, 0. So you would pick up these two terms when you multiply it out. So you would get e to the minus I phi over 2 cosine theta over 2. And let's see, this becomes up, down. That's the up component. And then there's a down component, which is this guy, e to the I phi over 2 sine theta over 2, down, down, right? And nothing happens to the second spin yet, right? It just stays down. We're just doing one of these terms. We'll combine both the terms later, but we're just doing one to show you how it works. Okay, now you have to do, now you have to rotate the second spin, which is pointing down. So the basis vector for that is, of course, 0, 1. So you pick up these terms. So what do we get? We get minus e minus I phi over 2 sine theta over 2. Then you have all this stuff. And this would be the up component, right? That's from this term, this is the upper component. So that would be the spin up component. From this term, you also get the spin down component. There, you would get e to the I phi over 2, right? Cosine theta over 2. And then it's the same coefficient here. And this would be up, down. And then what? Well, then you have this term right here that you rotate the second spin, and that's pointing down. So again, we pick up these two terms. So you get minus e minus I phi over 2 sine theta over 2. And now it's this coefficient, so it's e I phi over 2 sine theta over 2. And it's down, up, right? Because this is the up component of the second spin, rotating this guy. And then you'll finally get the last term, which is e I phi over 2 cosine theta over 2 sine theta over 2, and that's the down, down. Okay, so now stuff starts, we can combine things and start canceling various factors. So when these exponentials come in with opposite signs, they get canceled out. And so what you end up getting is you get these terms where you have sines and cosines, sine theta over 2, cosine theta over 2. And then you would have, and then these would combine to make minus e minus I phi up, up. And then there's plus e to the I phi down, down. That's those terms. And then you would also get the ones where the sines and cosines match up, which is plus cosine squared theta over 2 down, down, plus, not down, down, sorry. So here the cosine is up, down, and then the sine is down, up. Okay, that's good. So we have that, and now we just need to get the other term. But the other term, is there a question?
Minus sine squared.
Oh, yes. Nice. So the other term is easy because we just flip up and down, right? You don't have to really do anything because we can just exchange up and down to get this guy. So D2, D1 acting on down, up is sine theta over 2 cosine theta over 2. Then it's minus let's see, fine. Yeah, so actually the way to think about it is you just, so if this is spin 1 and this is spin 2, right, you can just flip, to get the second term, you just flip what you call spin 1 and 2. So you just exchange the two spins inside the ket, and that'll give you it. Yeah, that's the right way to do it. So you just exchange those two things. So this term actually doesn't change at all, because if we exchange these two guys, it's still up, up, and this is still down, down. You can alternatively just work out the algebra just like I did here, but this is a little bit faster to do it this way, of course. You can work it out, but it's just amounts to exchanging the spin 1 and 2. And then this is the same, except now instead of this being up, down, this is down, up. And this guy is going to be up, down. Okay, and now we can put it all together, right? We can put it all together. We can put it all together to see what happens to the singlet state. So D2, D1 acting on the singlet state is going to be 1 over square root of 2. And then we just combine these two terms. There's cosine squared theta over 2 up, down, minus sine squared theta over 2 down, up. And then you subtract off this guy, cosine squared theta over 2 down, up. And then you add sine squared theta over 2 down. And the up, up, and down, down pieces cancel, right? Because they're the same for these two guys. You know, we're subtracting them off. So what do we get? This cosine squared can combine with this guy. And you get 1 over square root of 2 up, down. And then this sine squared can combine with this cosine squared and you get minus down, up. So lo and behold, when you rotate the spin arbitrary angle, you get back out the same state. So this spin singlet, whatever it is spherically symmetric. Kind of amazing, actually. There's no way you could have, I mean, I don't know how you could have guessed that. If you think about it, it's just quite strange to have that to begin with. You're taking two spins that point in some direction and you're combining them in this entangled state, which is now spherically symmetric. We'll see the significance of that later, but still it's pretty surprising. And this just gives you a flavor of how to calculate with tensor product spaces. You just do things one at a time on each spin. The other one just comes along for the ride. That's generally how it works. Okay, any questions about that? We'll talk more about this when we do addition of angular momentum. But I wanted to give you just a flavor of the weirdness of having entangled states like this. They can have some strange properties. I think this, although people don't really talk about it this way, but this is a kind of strange property of it, right? That you put these two spins together and all of a sudden you got a completely spherically symmetric state. That's kind of surprising. But we'll see it all makes sense when we talk about addition of angular momentum. Any questions though?
I have a question.
Yeah.
So instead of just acting on each state individually, one at a time to compute it, could we find like a 4x4 matrix representation of D2 and D1 and just do it all in one fell swoop?
Yes, you could. Yes, you could.
Is it easy to find that representation or is it kind of tricky?
Well, I mean, it would be this thing. This would be the operation. And so you would need to, it's a little bit tricky because of your basis. You would need to recombine these things in such a way that, so you kind of know what, you'd have to figure out what the matrix does to all of these basis vectors. And you'd have to assign some states to all of these. So that's where it gets kind of tricky. It depends on how you assign states to these. So maybe this, you could say this is up, up, and this is up, down, and so on. But there's a couple, so that's how you could do it.
Gotcha.
Oh, so there's another question. When I first applied D1, how do you, when I first applied D1, yes. So D1, what happens? I'm working on the first spin. So the second one is always down. So the two terms are just, the second spin is always down. And then the first spin is up. So that's this vector 0, 1, or 1, 0. And when I multiply it by this matrix, I get a term here and a term here. And this term corresponds to the spin staying up. That's in the one, in the, you know, if you think about multiplying this out, you get a vector with two entries. This entry is for the spin up, that's this guy. And this one is for a spin down, where the first spin is down. It's just multiplying this and getting a vector with two components. But yeah, as I was saying, if you assign the basis vectors to these four, you know, to these four things appropriately, yeah, you could work out what this thing has to do as a 4x4 matrix in terms of these entries. You can certainly do that.
Gotcha. Thank you.
All right. Any more questions?
Yeah, I just had one question.
Yeah.
You just explained to the other person that the top, when you multiply the d1/2 with the up vector.
Yes.
What did you say you get at the top and the bottom?
Oh, well, so it's this 2x2 matrix times this. So
yeah,
you get, I mean, you get this entry. It's e to the minus I phi over 2 cosine theta over 2. And the one on the bottom is e to the I phi over 2 sine theta over 2, right?
Right.
So this is e to the minus I phi over 2 cosine theta over 2 up for the first spin plus, you know, the sine thing.
Got it.
Down. So that's what these two are. That's how you get the down, down.
Okay. Got it. Thank you.
Yep. Okay. Well, good. So now you have a sort of flavor of how it works. It's nice if you're very quick with converting between matrices and vectors and these kets. That's something I've been emphasizing throughout the class, is that they're all the same thing. It's just different notation, but it's good to know both. And to kind of use whichever one is convenient for a particular thing. Sometimes it's nice to think about matrix multiplication. Sometimes it's nice to just do the bras and kets. I mean, it depends. For things like these rotations, it's kind of easier for me to think about a rotation matrix, so like a 2x2 thing like that. But for other things, sometimes you just want to do the bras and kets, so on. But it's the same thing. And if you want to think about it as a 4x4 space, you could do that too, as I mentioned, as Jordan was asking. You know, you could just set up a basis of these four vectors, and they could be these guys, and then you could do everything in terms of 4x4 matrices. So that's also a possibility. So yeah, it's all the same thing. It's just different ways of looking at it. All right, I'll clear this then. So the reason why composite systems are also interesting, you know, other than like being able to combine multiple particles together, is that it lets you think about the system outside of just some fixed Hilbert space. But, you know, often if you have some system that's describable by some Hilbert space, it's not isolated. It might be in some environment, right? And the environment might have its own associated Hilbert space. And so then you might wonder what sort of the state of the whole system is as kind of a tensor product between the system that you're looking at and then the environment. This is environment. And oftentimes you actually don't know the environment. You don't know what state it's in. And so this leads to the idea of incorporating like classical uncertainty, in the sense that, remember what I told you, if you have a ket, right, and it describes the state of your system, this is the most amount of information you could possibly have about a system. This is most information possible. But often you're in a situation where you don't have that maximal amount of information. You don't know the pure state. You might know a set of pure states that it could be in. These are called pure states in this language. They're just kets, but okay, so what am I driving at is that it's convenient to, instead of thinking about kets, when you have this situation that you don't know which particular state you're in, maybe because the system is interacting with an environment for which you don't know the pure states, it's convenient to, instead of talking about these guys, to talk about the state operator. And in fact, you can formulate all of quantum mechanics in terms of just operators and kind of not even having the states. And the way you do it is you just, instead of thinking about this ket, you think about the projection operator onto the state. And so the equivalent of a system being in a ket psi would be that the system has this as its state operator. This is what describes the state. So it's just a different way of describing the state of a system. You don't describe it with a vector in a Hilbert space. You describe it as an operator, projection operator in the Hilbert space. And that allows you to generalize the concept of uncertainty, to go beyond just the quantum mechanical one that we've been thinking about, where we take this state, right, and then we calculate things like the probability of observing the state in a, or measuring a particular eigenvalue A, for the associated observable. And we talk about these as the probabilities. Well, you can do the same thing, but now with these state operators. And these are much nicer in a way, because, for instance, let's imagine we have an observable A. Then in terms of this matrix, we could calculate the expectation value of the observable. Easy to do, we sort of know what it is, right? It's psi, A, psi. And to get things going, we do the usual thing. We introduce completeness relations, in terms of whatever basis we're looking at here. Now these are all just numbers, and we can pull these guys around, right? We'll get M psi, psi, and AM, right? And just rearranging these inner products, flipping them around. The usual manipulation we've been doing all semester. Now you get rid of this completeness guy in here, and you get a sum over M, M, psi, psi, A, and then M. And if you think about it, this right here is rho A, right? It's the projection times A. So all this is it's just the trace of rho A. So if you want to calculate expectation values of observables, you just multiply them by your state operator and trace. Really nice, very compact way of doing things. And what else? So The other thing is you can generalize, you can introduce uncertainty, like classical uncertainty. Suppose you don't know which ket you're in. Then you can specify still the state of the system using the rho operator, but you just sum over the probability that you're in state alpha, or yeah, that you're in state psi alpha, and this is, you sum over all the ones that you're uncertain about. So this is the probability that you're in state psi alpha. So, and that's nice because then, it makes sense, right? Like the expectation value of A, in this case, what should it be? Well, if it were to make any sense, it should be sum over all the states we're uncertain about, the probability that we're in this state, and you average over the expectation values of, the states you're uncertain about, which one you're in. And you can check, you can check for yourself that this is indeed just trace rho A again with this form of rho. Pretty straightforward to show, just as I just did with the basis. So it's nicer. The description of a state as just a simple ket is limited because it doesn't allow the possibility for you to be sort of uncertain about which ket you're in. And the state operator is much nicer because it combines both classical and quantum uncertainty. Is I think a good way to think about it. Any questions about that? We'll do examples. We'll talk about rho, in a lot of detail. But that's the basic idea, is that instead of just a ket now, you can have a probability distribution over being, for being in any number of kets. All right, so that's the definition, and now we could talk about sort of properties. This is a sort of definition of rho. This is a general one, and now we can talk about the properties of rho. There's a couple. Obviously, if you dagger this thing, right, the dagger can't do anything because it'll just flip the bra to a ket and vice versa. So it's Hermitian because the probabilities are real numbers. So if you dagger it, nothing happens. The other important thing is if you take the trace of just rho by itself, well, then you should get that it's the sum of these probabilities, right? You can imagine picking a basis where these guys are the basis, the diagonal. Then if you diagonalize your rho, right, then the entries on the diagonal would be the probability that you're in a basis vector, or in one of those kets corresponding to the basis vectors. And in that case, yeah.
I did a question. So in that case, if let's say it is simple 2 by 2 and it was 1 0 0 1, you're saying I take the diagonal of that, which is 2 because it's a trace of it, and that would be my probability value, correct?
No. So rho in general is going to be an n by n matrix.
Oh, okay.
And suppose we diagonalize it, we find some basis for it. What would it look like? The form of it would be sum over the eigenvalues I, lambda I, and then it would be the basis vectors, which I guess I'll call II. And if I think about that, that would mean that these guys must be, sort of by definition, the probabilities.
I see.
It's the probability you are in ket I. That's because it would be diagonal matrix. Those would be the entries. They'd just be on the diagonal.
Right.
And so that means if you take the trace, you have to be in, you know, one of the kets. So the probability has to sum up to 1. So the trace of rho has to be 1 because it gives you the probability of being in a particular ket when it's diagonal.
Right.
So that makes sense too. The other thing,
Sorry.
When rho is diagonal, then the trace of rho is always 1.
the trace of rho is independent of the basis, remember? So if it's diagonal and it's 1, then if it's not diagonal, then it's also 1, right? We proved that in the homework.
Okay.
Yeah, it has to be 1 because of, okay, so I mean, first you'll agree that from the definition, it has to be Hermitian. If it's Hermitian, then you can diagonalize it. If you can diagonalize it, you can always write it in this form.
Yes, I follow.
And then once it's in this form, you know what it means. The only thing this could possibly mean is that you're in probability lambda I of being in state I. Mm-hmm. Because then it's just a diagonal matrix, and that's, you know, that's the only way to interpret it. And if that's the case, then these lambda i's must sum to 1 because probability has to sum to 1.
Okay.
So then the trace of rho has to be 1, just logically speaking.
So the assumption is that we are in finite dimensional Hilbert space?
No, not, well, yes, for now, I guess. I don't think any of this fails in an infinite dimensional space. I think all this is still okay.
Yeah, so because the index set alpha, so the index set can be countable infinite, right?
No, yeah, no, so yeah, it's kind of tricky. Technically, even in an infinite dimensional space, there's going to be a countably infinite basis always. That's something I tried to emphasize when we looked at that chapter. But the rho, you might not want to think about it in that basis. You might want to think about it in a basis that's a pseudo eigenbasis. So you might want to think about it in coordinate representation, and then it would be like a density type function. So, but we won't get into that. So for now, yeah, let's just imagine we're in finite dimensional space. Although I think it's all the same for infinite. These properties are still all the same. Yeah. And the other thing, of course, is that if you take the expectation value of rho, well, I mean, this is always positive. So it's a positive operator. It's because probability is positive. So this is also something you can prove pretty easily. And last but not least, rho describes a pure state, meaning that, you know, it's equal to some single projection to a single state. If the only way that happens is if rho squared is equal to rho. You can show that also. You can sort of see that it's sort of, you know, it's pretty obvious here. If you know, if rho is equal to this, then of course, you know, you multiply it out like that, and it's just, you get back to where you started. So, but there's more to it. There's more to it than that. You have to show it the other way. You have to assume that if this is true, then you should be able to show that rho is a pure state. But won't do it. It's just a property of the state. just a property of the state. And those are the four things. And yeah, so now let's do any questions though about that before we do examples.
Would you please remind me what was the pure state? Like, is it satisfy the probability to be equal to 1?
A pure state means that rho has this form, that it's a bra and a ket of just a single state, a single vector in a Hilbert space. If you can't write it this way, then you can write it this way. There's just two options, right? There's two options for rho. Either rho is like this, and that's a pure state. If there is some state for which you can write it like that, or there is no such thing, and then you can always write it as a sum over things like that. And then this is a probability of being in one of those states, and then this is a mixed state. Those are the only two possibilities. A pure state is a state of no uncertainty. The only uncertainty in it is the quantum mechanical uncertainty. A mixed state is always, you're like lacking some knowledge that you could in principle have. So there's some uncertainty here. And those are the physically, those are physically the differences between the two. All right, so let's do examples.
I have I know you're going to do an example, but in that rho as a pure state, it has to be equal to 1 in order to be a pure state. If it's less than, it would not be a pure state, right? If it was less than 1, less than or equal to 1, it has to be equal to 1 to be a pure state.
What has to be equal to 1?
That rho squared. Like, you see rho is a pure state if rho squared equals p rho.
Yes,
now,
yeah.
Isn't that like, isn't there like a, that's an if then, that it has to be, if the trace of the rho squared is less than 1, then it's not, right? Because you'd have to show that by contradiction. But if it is equal to 1, it has to be a pure state. Is that right?
I think it's an if and only if, actually. If
Okay.
it's a pure state, then this is true. If this is true, then it's a pure state. So they're equivalent.
I see. Okay. Thank you.
Okay. So an example would be just our spin 1/2 particle, just one this time. So it's kind of funny. We did composite spaces for a bit. And now we're doing this state vector thing. And they're, I know it's conceptually kind of annoying because we're sort of not doing a composite thing for now, but we will in a moment. It's just for now, we're introducing this new object. But again, remember the motivation of even introducing the object is because in the end, we want to be able to describe our system, right, in terms of a state operator in such a way that we incorporate, for instance, our uncertainty about the environment. And then that's where the composite part comes in. If we treat the whole thing as a composite system, maybe the whole composite system is in a pure state, a tensor product state. And if we somehow can sum over all the uncertainty that we have about the environment by like summing over, say, the probabilities, something like that. We'll see how exactly later, but then you would have a state operator describing just the system here. So that's the connection, but we have to build up the state operator stuff first before we get there. Oops.
Yeah, that really helps actually. Thanks for making that connection.
Okay. Yeah. Yeah, I think it was confusing last time around I did this, so I want to make sure to emphasize this is it's different. It's not doing tensor products, we're just doing a state operator for now. So spin 1/2, we're back to two-dimensional Hilbert space. And so rho, you know, we know that trace of rho is 1 and it's Hermitian. So rho is very constrained already just from those conditions. If this is an A, then this must be 1 minus A because the trace. And it's Hermitian, so A is real. And then the only other possibility that it might be an off-diagonal term, but if that's C, some complex number, this must be C star because it's Hermitian. So already the state of a spin 1/2 particle, the most general state incorporating all kinds of uncertainties, already down to just 3 numbers, the real and imaginary parts of C and A. But even that is constrained because if we take the determinant of rho, that's equal to the product of the eigenvalues. And since this is a positive, this is a positive matrix, then this has to be greater or equal to 0. So that gives us a constraint on these C's. It tells us these C's and A's, it tells us that A times 1 minus A minus the magnitude of C squared is greater or equal to 0. And moreover, we know that because of the trace condition, lambda 1 must be equal to 1 minus lambda 2. We also know that. And so in general, then this product, right, I could write it lambda 1 times lambda 2 is also equal to lambda 1 minus lambda 1. And if you plot this thing as a function of lambda 1, right, it's got a peak. It vanishes at 0 and 1. And it's got a peak at 1/2, right? So it's 0 at 1 and 0, and then it's maximized at 1/2. So this actually also not only has a lower bound, it's got an upper bound of where both of these are equal to 1/2. So this is less than or equal to 1/2 times 1/2, which is 1/4. So this is very constrained. It's it's greater or equal to 0. And it's also less than or equal to 1/4. So it's bound quite a bit. And okay, so let's think about this some more. We can actually write this in terms of the Pauli matrices, as we've sort of been doing on the homework and stuff. You can take any 2x2 guy and write it as a sum over the Pauli matrices. And you can show that, again, you have 3 degrees of freedom here. And we know we also have this constraint. And we'll see what that looks like in terms of the Pauli matrices. But the idea is that you can rewrite this in terms of the Pauli matrices as follows. It's actually going to be equal to 1/2 times the identity plus B dotted into the vector of Pauli matrices, where B is now a vector of real numbers. It's not obvious, but you can do it just like we did on the homework. You can expand this in the Pauli matrices, you know, and you get a 2x2 matrix, and you can just see how the coefficients of this B vector are connected to these coefficients here. But some things should be obvious right away, like the trace condition. The trace of the identity here is just 2, and 2 over 2 is 1, and the Pauli matrices have 0 trace, so this just gives you 0 trace. So you can make this connection. Well, we can actually just, if you were to do that, you would get 1/2, and then on the diagonals, you get 1 plus BZ, the Z component, that's from the Z Pauli matrix. And here you get 1 minus BZ, that's from the -1 of the Pauli matrix. The off diagonals are the X and Y components. And this would give you this kind of thing. Yeah, so I guess it's kind of obvious what's going on here, right? A is equal to 1 plus BZ. And C is just equal to BX minus IBY. So it's a direct mapping between the two forms. And what else? We can actually compute the determinant of rho. And what is that? That's this 1/2 squared, so that's a quarter. And then you get this guy times this guy, which is 1 minus BZ squared. And then you get minus these two guys multiplied together. That just gives you minus BX squared minus BY squared. So that whole thing is 1/4, 1 minus the magnitude of this B vector squared. And we know that this thing, right? We know that's this condition. So this tells us then that 1 minus B squared lives between 0 and 1, right? Yeah. Or if you want, that's the same as saying B squared. Well, this part's obvious because it's the magnitude. Yeah, but this just means that you can rearrange this, right, and get this condition, that the magnitude of B squared is less than or equal to 1. So the state of a spin 1/2 system including all uncertainties that are captured by the state operator, all those states are described by a vector B, right, with 3 components. And that vector lives inside the unit sphere, right? And that's called the Bloch sphere. So if I were to plot all the different possible B's that you can have, they would live inside a ball, right, of radius 1. And the intuition is kind of the following: if the B lives somewhere on the surface of this ball, and the magnitude of B is equal to 1, then what would that mean? If you go back here, that means that the determinant vanishes. So it means one of the eigenvalues of your density matrix, right, is 0. And so the other eigenvalue must be 1, because they have to sum to 1. So that means you're in a pure state, right? Because that would mean that if the determinant of rho vanishes, right, then you must have one of the eigenvalues be 1 and the other one is 0. So that means you could write rho as the projection onto that eigenvector corresponding to this one eigenvalue, you know, psi 1, psi 1. So it's a pure state. So if the determinant of rho vanishes, or alternatively, if B lives on the surface of the sphere, then you're in a pure state. So it's like all the pure states live on the surface. And all of the mixed states, when you have some uncertainty, they all live inside that sphere somewhere. And the closer you get to sort of the origin of the sphere, that's, you know, so you can, okay, so if B, say you're at the origin, right? What if B is equal to 0? And if you go back here, b is equal to 0, then rho is just has a very simple form. It's just diagonal with halves on the here. And this represents sort of maximal uncertainty, right? Because there's a 50-50 chance of being in either, you know, the up or down state. And it's moreover, it's independent of the basis you use. If you rotate this around however you want, it'll still be the identity matrix, right? You can take rho and rotate it with some unitary to change the measurement, how you're measuring your spin. And no matter what you do, if you know you rotate it, you'll still just get back the same thing. You'll get the identity with halves on the diagonal. So it's a state of maximal uncertainty. No matter how you measure the spin, you don't know if it's going to point up or down. So pure states, they're on the surface. That's least uncertainty, remember. And then there's a point at the origin, you know, at 0, 0, that's most uncertainty. That's where you don't know. That's when you don't know anything about the spin. It's sort of, we call it an unpolarized spin. You have some beam of electrons, say, that come out of there. If you don't know anything about the beam or how it's, you know, if you don't prepare, you don't align the electrons in any fashion, then you don't know anything about it. So your state, your knowledge about that spin has maximal uncertainty. You don't know which way the spin is going to point when you measure it in a sort of maximal way. Even though, you know, it's very important to distinguish that from the quantum mechanical uncertainty of, say, measuring a spin that's pointing along the x-axis. You know that when you measure it along the z-axis, you don't know if it's going to point up or down, right? So it's going to point up or down with equal probability. But that's very different from sort of actually not knowing which way. So it's worth it to think about that, the difference between the quantum mechanical uncertainty and you know, classical uncertainty. Okay. Let's see. What else? So we could calculate the expectation value of the spin in any particular direction. That's, of course, the trace of rho times the spin in that direction. And now you can use the properties of the Pauli matrices. This is just the trace of H bar over 4. So the trace, this part of it, the identity piece, if we multiply it by, remember SI is just H bar over 2 times the Pauli matrix. So this part, since the Pauli matrices are traceless, that doesn't give you anything. So the only part that gives you something are these guys. And those are H bar over 4 times B, let's see, B sub J, sigma J. You have to sum over the J's, I guess, and then it's sigma I. And now you can use a property of the Pauli matrices that the trace of sigma I, sigma J is equal to 2 delta Ij. So this becomes 2 H bar over 4 Bi sigma I. And so the 2's here cancel, and you just get that it's, well, you just get that it's H bar over 2, right? Sigma I Bi. So it just tells you that and H bar sigma I is that component of S. So the BIs tell you, you know, the magnitude of the spin along the I direction. So another way to write this would be the expectation value of the spin vector is equal to h bar over 2 b vector, where now this is interpreted in terms of the sigmas, right? This is a vector with bx, sigma x, this kind of thing. So the expectation value of the spin operator is going to be given by this b vector. It tells you, the Bloch sphere tells you roughly the direction in which the spin is pointing, right? And if it's living on the unit sphere, then it gives you the actual direction it's pointing in, so that when you measure along that direction, you always get, you know, plus h bar over 2. But as you make that vector size smaller, that tells you the uncertainty that you have about it, the fact that it's pointing in that direction. So that's how it works. And in principle, the other thing I wanted to mention is if you have a mixed state, then the particular mixture, remember a mixed state is a sum over some kets like this. But unfortunately, this is not unique. There are multiple ways of writing a given state matrix, and you can really illustrate that in using the Bloch sphere. And I'll show you how in a moment. But any questions before I do that? General questions about what the Bloch sphere is about?
No, but that b value you set, of course, it'd be trivial if it was 0, right? Or that would say that all those values there would be 0. So we would definitely not know. But if it's equal to 1, then one of those spin directions would be that we'd have to calculate, because it's not going to be in X, Y, or Z, right? It's going to be spinning.
If B is 1, the statement is the following. If the magnitude of B is 1, then there is a measurement you can make which would give you a value of h bar over 2 with 100% probability, right? It means that the spin is pointing in some direction. And so there is in principle a measurement you could do to get with 100% certainty that spin direction. If B is 0, then you can't do any measurement on it to get a value of h bar over 2 with any certainty beyond 50-50. It's not pointing anywhere. The expectation value of the spin operator is 0.
Yeah.
It's pointing in all. It's, you know, it's like doing an experiment with like an unpolarized beam of electrons. Say each one comes out with just a random orientation of the spin, and you know, we just don't know which one it is, and each time it's random. So if you average over all of them, you'll always get you know 0 for the total spin expectation. Yeah.
Which makes sense from what you described before, because that's our uncertainty. Then we wouldn't know how it's going to come out, what spin it is if it's 0. You know.
Yeah, and I wanted to kind of make sure you understand the difference between that and the following, where you say you send in a spin that's like pointing along the y hat direction, and you put it in a magnetic field gradient, right, that measures along the z hat direction. And when you know that when it comes out here, it'll be a 50-50 chance of being plus h bar over 2 or minus h bar over 2. But you see, that uncertainty is very different from the sort of mixed state uncertainty. It's very different because in this case, you know, the spin actually is oriented along the y hat direction. And if you know, were to rotate your apparatus so that it measures along y instead, then you would get, you know, plus h bar over 2 with 100% certainty.
Yeah. Okay, I got that. Thank you.
Okay, and the thing I wanted to mention is that this decomposition is not unique, unfortunately. Well, I don't know, it's just the way it is. So the probability distribution that you pick here, there's many different ways of choosing that. There's not just one way. Because if you think about it, say you have your sphere. your Bloch sphere, like this. And say you have your B vector, which is inside here, which isn't at the surface, so it describes a mixed state. What you can do is you can pick a core, you can pick any chord that goes to 2 points on the surface. So you could pick 2 points on the surface, N1 hat, and say, well, okay, so you have to pick a chord that kind of, this, I mean, it's a bad drawing, so. You have to pick a chord that runs from the tip out here perpendicular to this thing. And so on the surface, it would describe this kind of circle, all the different choices for this chord. It's just a chord that runs perpendicular to the vector and reaches the tips of, reaches the surface of the sphere here. And so there's two directions, two pure directions here, and one hat and two hat that go to the surface, like this. And how we can describe this state with this particular B as the following. We could describe it as rho is equal to 1/2. And so the idea is, how would you get to this point? Well, what you could do is this vector B, just use some geometry here. The vector B must be this vector N1 hat plus, what you would do is you could write it as some distance lambda times the difference in the two directions, right? So N2 minus N1 would give you something along this chord direction, I guess this way. And so then the B vector, the way you could get from here to here, could also be just going up by N1, then over by some distance lambda times the difference between these two vectors. So this is just some vector addition. So to get from the origin to here, you could just go by B, but you could also go up by N1 and over by lambda, some distance, N2 minus N1. And so then your rho matrix, sorry, I'm going to run over a little bit, but I'll just finish this thought. It's just given by 1 minus lambda times the direction along N1 plus 1/2 lambda direction along N2. Because this I can write as, right, this is 1 minus lambda N1 hat plus lambda N2 hat. So I can, the equivalent rho matrix for that particular B, I can just write as a combination of these two things. And what that means is, if I write out what this is, what I'll get is that this is equal to 1 minus lambda, and it's the projection, it's the plus H bar projector, pure state, plus lambda, because now these live on the surface, right? So these are pure state operators, so they must correspond to pure states. And here we get the N2 direction. So you see, we get a mixture of these two directions, N1 and N2, with the probabilities given by this distance that you have to go to get back to, where the B is located. But that chord, we could have chosen this chord any way we wanted, as long as it's, living on this circle on the surface, right? So there's an infinite set of different mixtures that we could have picked. mixtures of these two directions, because we could have picked this chord in some other direction and we would have gotten two different pure states as our mixture. So there's lots of different mixtures that correspond to the same B vector. And that's the idea, and that's why these mixed states are not unique. But see what happens as B gets closer and closer to the surface. As it gets closer and closer to the surface, the number of chords that you have gets smaller and smaller, right? Because as you get really close, as B gets really close to the surface, you can, then the chord is very small that you get. And so then your possible choices are on like a small circle on the surface. So there's less and less freedom of choice there as you get closer to a pure state. And of course, once you're in a pure state, then, this will just be given by one of these projection operators. So that's the idea. We'll talk more about it next time, I guess. And next time I'll combine all this with composite systems, and then you'll see how the two things connect together. Yeah, that's it for now.